All right, guys, we're starting down here in the middle with sequences. So a sequence is an ordered list of numbers. A finite sequence is a function that has a limited number of terms and whose domain is the finite set of 1, 2, 3, 4, 5, all of these numbers. The values in the range are called the terms of the sequence. So like when we're trying to find a pattern or a sequence, we're talking about these are always going to be the domain numbers, and the output numbers that we get are going to be called a sub 1. So that would mean the first term. A sub 2, second term, third term, fourth term, nth term. Okay? Now, an infinite sequence is a function that continues without stopping and whose domain is the set of positive integers. So here are examples of finite sequence and infinite sequence. So a finite sequence is going to go 2, 4, 6, 8, and then it stops. An infinite sequence goes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, goes on forever. So that's the difference. Whenever you see these dots, it's infinite. It means that it continues forever and ever. A sequence can be specified by an equation or a rule. For example, both sequences above can be described by the rule a sub n equals 2n or f of n equals 2n. Do you see how this is the first term? This is the second term, third term, fourth term. So that's telling me what n equals. So n equals 1. 2 times 1 is 2. N equals 2. 2 times 2 equals 4. Okay? So now we're going to do this both ways. So if I give you a sub n equals negative 2n plus 3, we're going to find a sub 1, a sub 2, and a sub 10. So a sub 1 means the first term. So we're going to plug 1 in for n. What do we get? 1. We're going to plug 2 in for n. What do we get? Let's squeeze in a sub 3. I want to do one more in there. A sub 3, what are we going to get? Negative 3. A sub 10 now, if we plug in 10, what do we get? 17, right? So can you see now what this pattern would be? This pattern would go 1, negative 1, negative 3, negative 5, negative 7, dot, 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 right? So can you see how in the warm-ups I gave you this pattern and I asked you to come up with this rule? That's what I asked you to do on numbers 4 and 5. What's the difference here between these? What are we doing every time? We're taking away 2, aren't we? And that's why it's negative 2n. And then I have to think, well, negative 2 times 1 is negative 2, but I want to get a positive 1 in that spot. So I have to make it plus 3. Okay? So now I'm going to give you guys a pattern, and I want you guys to try to, from the pattern, come up with this rule right here. So here's your second example. That was number 1. This is number 2. The pattern's going to go 5, 2, negative 1, negative 4, dot, dot, dot. What would the rule be for that? So this would be when n equals 1, n equals 2, 3, 4. Who has it? Alex, what'd you get? Plus what? So now I'm going to check that. If n equals 1, negative 3 times 1 is negative 3 plus 8, that's 5. That works. Test it for 2. Negative 3 times 2 is negative 6 plus 8, that's 2. That works. Very good. So this is the correct formula. That's going to be the rule for a sub n. Questions? All right, let's do one more of those. All right, so let's say that we've got 7, 11, 15, 19, etc. What's the rule going to be? Chloe, what'd you get?
4n plus 3.
Do we agree? Yep, that works, doesn't it? We would have to check. This is our when n is 1, n is 2, n is 3, n is 4. I'm just going to check n is 4. 4 times 4 is 16, plus 3 is 19. Yes, it works. Okay? All right, let's go over, let's go back up to the top then. So a sequence is just a pattern of numbers. The terms of the sequence, these are going to be the output. So these numbers here are called the terms of the sequence because they're the output that we get. All right, now let's go over to page 219. And we're going to have another term here, and this term is series. The last thing we did was called a sequence. It was just a pattern of numbers. Now, a series says when the terms of a sequence are added together, the resulting expression is called a series. A series can be finite or infinite. So a finite series is 2 plus 4 plus 6 plus 8. An infinite series just means it's 2 plus all of these, but it goes on forever. What would be the sum of an infinite series? Infinity, yes, because it goes on forever. So for an infinite series where we're getting larger every time, that sum is going to be infinity. Now, if we were getting smaller every time, that's not going to be the case, but we'll get to that at a later time. So you can use summation notation to write a series. For example, the two series above can be written in summation notation as follows. All right, now this can be a little confusing, so watch closely. This right here, this is called sigma, okay? It's a Greek letter, sigma, and in math it means the sum. And here's the way it works. This is saying that we're going to let I equal 1. Right here, this is saying let I equal 1, 2, 3, and 4. That's what it means. When it says the sum as I goes from 1 to 4. So it's saying to let I be 1. So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. All right, so that's the way we write that. Now, look at the difference. It's the same thing. It's still 2i, because this is 2 times 1, 2 times 2, 2 times 3, 2 times 4. But look now. It's saying we're going to go from I equals 1 to infinity. Okay, so doesn't that make sense? This is telling us what's the last number to use, and this is telling us what's the last number to use. So for both series, the index of summation is I. That's just the variable that we're using. You can use any index. I tend to use n. You'll see me use n a lot. Some people use x. We typically stay away from x, and that's just because it's more standard with y equals mx plus b. So we tend to use i's and n's a little bit more for this. But the lower limit is called 1. The upper limit is 4 for this that we did up here. And then the upper limit on this one is infinity. Summation notation is also called sigma notation because it uses the uppercase Greek letter sigma, which is written like that. All right, so now let's look at a couple of these. So let's say we have the sum as n goes from 2 to 6 of 3n minus 1. Well, here's what this would mean. I have to use n equals 2, 3, 4, 5, and 6. Those are the n values I have to use because I'm starting at 2, I'm ending at 6. So I plug in 2, 3 times 2 is 6, minus 1 is 5, plus, plug in 3. That's 9 minus 1, that's 8, plus, plug in 4. That's going to be 3 times 4 is 12, minus 1 is 11. And now I can see the pattern. I'm just adding 3 every time. Okay, so that would be how I do that problem. And I can just get out a calculator if I need to. Those aren't that large of numbers, but 5 plus 8 plus 11 plus 14 plus 17. And that's 55. Well, now I'm going to show you a really cool way that we can do this. The calculator has this symbol on it. Hopefully you have a newer calculator. If you have an older calculator, it's going to be a little bit tougher. Go under Math and arrow up. Do you see summation on your calculator? If so, you're in luck. If not, I will show you how to do it the other way. All right, so those of you who have summation, go ahead and hit enter. And we can just type this in exactly how we see it. I have to put in the letter N, so I have to go to alpha, and then I have to find the N in blue, which is right here. So I'm going to go from N equals 2 up to 6, and then I'm just going to tell it the function. 3, go back to alpha, get the N, minus 1. See what I've done? I've just said I'm going to go, I want the sum from N equals 2 to 6 of this function. I hit enter, and it gives me that answer. And I don't even have to write anything in. Now, if you don't have that, well, you have to find the sum under your catalog. This catalog down here has everything that's on our calculator. So I'm going to have to go second catalog. Now, this has everything on our calculator. If I sit here and scroll, it's going to take me forever to get to the letter S. I mean, I can do it, but it takes too long. So it'll jump to S if I find the S. Right there's S. I'm going to push that button. That'll take me directly to the S's. And I got to find sum because I want the sum. It's still pretty far down there. There we go. So, ooh, I haven't seen that. That's probably not on yours. If you have an older one, does anyone see this summation or not? Even with an older calculator? Who up? No, Kara? Okay, so let's go to this, to sum. We're going to use this one. So we have to do the sum of the sequence. So now I have to go back to my catalog, jump back down to the S's, because I have to tell it to do the sum of this sequence. And then I have to tell it what is the sequence. I'm going to just use X's. 3x minus 1, comma. Now I have to tell it what's my index that I'm using. I'm using an index of X, comma. Now I have to tell it where to start. It's starting at 2, comma, and where it's ending. It's ending at 6. And now when I hit enter, it's going to give me the answer. Some of you are thinking you might want to go out and buy a new calculator, right? Or just borrow somebody's when we have a test. But guys, here's the good news. If you got this typed in now, let's say that I sit here and I do all this other math and I've done this stuff for like 5 days even. Remember that even though I've done all of this, let's say I forget how to find my sum and sequence and I have this older calculator. Watch. Second enter, second enter, second enter. It can remember, oops, there it is. I better stop. And now I can just edit this because I already have that sum and sequence. Do you see what I'm saying? Like it just remembers everything that I've done. So now I don't have to retype that in. Okay, and I'll help you one-on-one if you need it with that, with setting that up. All right. So now we know both ways of doing that. So these are some special formulas. We're not really going to use these anyway, so let's not worry about those. Flip over on the back. Okay, so it says to write the first 6 terms of the sequence. We're going to do the first 4 terms. So we're going to find a sub 1, a sub 2, a sub 3, and a sub 4. So that just means we're going to be plugging in these numbers. 1, 2, 3, 4. What do we get if we plug in 1? 0, 2, 7, 3, 4. Okay? Now, think about this. What if you had seen this pattern? 0, 7, 26, 63. Would you have recognized that it was that formula? Probably not right off, would you? So you can see how some of these patterns would be difficult to go from this way to that way. But if you really think about it, adding 1, see how this would be like 1 cubed minus 1, 2 cubed minus 1. Like maybe with enough practice you could come up with this if you were given that pattern. All right, the next one. F of 1, F of 2, F of 3, F of 4. So I have to plug in 1. 1 minus 1 is 0. So this would be negative 2 to the 0. What is that? 1. Negative 2, I have to plug in 2. 2 minus 1 is 1. What's that going to be? Negative 2. Now we're going to have negative 2 to the 3 minus 1. That's 2. Negative 2 squared is 4. And then negative 2, 4 minus 1 is 3. What do you get if you cube a negative? Negative. Negative 8. Guys, look at this. When we want these signs to alternate, positive, negative, we have to have a negative that's getting raised to a power. See, that's what forces these signs to go positive, negative, positive, negative. On the ACTs, a lot of times you'll see that, where the signs alternate. And what's going to cause that to happen is having a negative number raised to a power. All right, back to the old type that we did earlier. Describe the pattern, write the next term, and write a rule for the nth term. Let's look at the pattern. What's happening every time, guys? You don't have to write out the description, but we're adding 2, right? So what's the next term? 5. Okay, so we did the next term. Now write a rule. Think about it. Think about what we said. Whatever we're adding on, that's what we're going to have as our multiplier. So how am I going to start this? 2n. So for my first term, when n is 1, though, I have to get negative 3. 2 times 1 is 2. How am I going to get negative 3 out of that? Jonathan? Subtract 5. Now check it. See if it works for the second term. 2 times 2 is 4, minus 5. Is that going to give us the right answer? Yes. So this is it. All right, let's look at the next one. What are we adding on every time here, guys? 2/5, right? So this is just going to be a sub n equals what? 2/5 n, right? See if it works. N is 1, n is 2, n is 3, n is 4. 2/5 times 1, yeah. 2/5 times 2, yes. 2/5 times 3, right? Because this is 3 over 1, so that would work. Okay, tough stuff here now, guys. Look. See how this is alternating? Negative, positive, negative, positive, negative. Ignore the negative and positives. What are these? What types of numbers are they? Squared, right? They're squared numbers. So it says to write the series using summation notation. That's where we use the sum, the sigma. Where is this starting? N equals 1. Where is it ending if it goes dot, dot, dot? Infinity, right? So what's happening every time? The 1 is getting what? Squared, right? So it's going to be n squared. But something else is happening too. The signs alternate. They go negative, positive, negative, positive. That means I'm going to have a negative 1 raised to a power. See if this works now. If I plug in negative 1 to the first, is negative 1 to the first positive or negative? Negative. Is my first term negative? Yeah. What about my second term? Negative 1 to the second. That's positive. Is my second term positive? Yes. Negative 1 squared is positive. Look at the third term. Let's check the third term all the way through. So my third term, n is 3. 3 squared is 9. That part works. Negative 1 to the third. Is that going to make it a negative? Is the negative to the third power negative? Yeah. So that works, doesn't it? That would be the summation for that problem. Okay? Let's have you guys try one now. I'm going to write out a pattern. Here's your pattern. It's going to go 4 minus 9 plus 16 minus 25 plus 36. That's your pattern. See if you can figure it out. How would it look in summation notation? As soon as you think you have it, raise your hand. Alex? Six. Okay, that would work. Say it again. That would work, wouldn't it? N squared, he's starting with 2, ending with 6, 2, 3, 4, 5, 6. So that part works. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Then we have to check his signs. Negative 1 to the n. That would work because negative 1 squared is going to be positive. Very good. Anybody come up with a different one, Chloe?
Well, I just have a question.
Yep.
How do you know the search with 2?
Well, you can make it start with whatever you want to make it start with. He chose to make it start with 2. Now, I could force you, I could say that you have to start with 1, and that would make the problem a lot harder if I made you start at 1. Now, think about it. If this has to represent n as 1, 2, 3, 4, 5, so now we would end at 5. This would no longer be 1 squared. So what would I have to write it as? Think, guys, what would I have to do to my n to get 4? Alex? But I'm still going to have to, it's got to work for all of them. Jonathan? So you're saying I could have done n plus 1 and then what? Okay, let's see if that works. So if I do 1 plus 1, that's 2. Is 2 squared 4? Yeah. Here's my second term. 2 plus 1 is 3. 3 squared is 9. See, this is when n equals 1, 2, 3, 4, 5. Let's check this one. 5 plus 1 is 6. 6 squared is 36. That works, doesn't it? But now I have to make these signs change every time. So it has to be times negative 1. Can I just do to the n? Look, if n is 1, negative 1 to the first, is that going to make that the positive? So what am I going to have to do with it, McKenna? To the n. You look like you were right with me on that. Well, it doesn't, but I'm saying that sometimes in the book they're going to have it written like this. They're going to say you have to start at n equals 1. Say it again. Would that work? Let's see. If we do -1 to, well, that would make it flip over. You know, if you raise something to a negative, it would flip it over. But you're on the right track with that. Alex? Added 1, yep. Wow, Alex, this is like your specialty. You should be a sequence of some guy in the... Yes. Okay, he's right. If I do n plus 1, -1 to the 1 plus 1 would give me 2. Is -1 squared going to make that a positive like we need it to be? Yes. All right. Guys, I know this is hard for some of you. I remember when I first learned this, it seemed really difficult. But I promise, as you practice, after you practice your homework, it will make so much more sense. Let me write this for you, though. If you want your signs to alternate, if we want our signs to alternate, we have to use a -1 to the n or a -1 to the n plus 1. That's what's going to force the signs to alternate, plus minus, plus minus, plus minus. Okay? In fact, we could even take this further. If we start off with -1 to the first, that's going to be if we wanted it to start off negative, right? Because -1 to the first is negative. And this would be if we wanted it to, the first sign to be positive. Because -1 to the second would be positive. Okay, we got to go. I'm talking too much. Let's go on to this one. We have to find the sum from 2 to 5, so I'm going to plug in 2. 2 over 2 minus 1, that's 1. Plus, so that's when n is 2. Now I have to do 3. 3 over 3 minus 1 is 2. Plus, now I have to do 4. 4 over 4 minus 1 is 3. Now I have to do 5. 5 over 5 minus 1 is 4. So I just have to add those numbers. And then I'll show you another way to do it. And we get this. We're going to math frac it. 73 over 12. Everybody see what I'm doing there? I'm just plugging in the numbers from n equals 2, 3, 4, 5. Getting answers, and this means the sum. This means to add them all. Now, I also could have done it like this. Since I have this kind of calculator, I could go math. I can go up to my summation. I can say I want to go from n equals 2 to 5 of, I would rather just use x. I should have just used x. You don't have to push this n all the time then. N divided by parentheses n minus 1. So I could have put it in like this and then pushed enter. I get that. I math frac it. I get the same thing. You see what I mean? Two ways of doing it. Write it out or don't write it out. On this one, am I going to want to write this out? Not really, because I have to do 1 squared, 2 squared, 3 squared, 4 squared, all the way up to 18. That's going to be way too long to do. So just use your summation on it. Hello. Okay. And we need to go to the office at the end of the period. Okay, so watch what I'm going to do, guys. I'm not even going to bother typing my summation in again. I'm going to do second enter, second enter. And I'm just going to put this in. Now I want my n to go from 1 to 18. Actually, I'm going to show you how to do it with the x's. That n's getting annoying. Summation. Here's my x. X is so much easier to do. X goes from 1 to 18 of x squared. I would always stick with x's. Those n's and i's are too hard to get to. 2109. All right? Get the basic idea? A sequence is a pattern of numbers. The sigma means to add up all those numbers. Okay? Good job, guys.